Hello students, so today I will give a lecture on spintronics. I've given previous lectures on spintronics, so I will introduce and then I will talk about a specific spintronic device. So spintronics, as the word suggests, is spin-based electronics. That means it deals with spin-dependent properties of an electron instead of charge-dependent. Spin-dependent properties of electron instead of charge-dependent. Now, directional and coordinate motion of electron spin circulates a spin current which will carry or transport information and control a spin in a spintronic device. So, as you know that an electron revolves around the nucleus, and it has been observed that electron has an axis of its own and it revolves around that axis. So there are two types of motion. One is orbital motion and one is spin motion. Now before coming to the details, let us first discuss that there has been a law suggested by Murray which says that the number of transistors on a silicon chip will roughly double of every 18 months, but with the discovery of non-electron devices, the dimensions are further reducing, so the development of heat is increasing more at accelerating rate than predicted by Murray, and also there are some new phenomena due to quantum effects due to the reduced size of the devices. So these two conditions, they are actually not tallying with what Murray said, so it's actually failing the Murray's law. Okay, now we come back to the electronic spintronic devices. Now, if an electron is spins, it can spin either in clockwise or in anti-clockwise direction. So suppose an electron is spin in this direction like this. So in this case, it would produce a magnet with the south pole on the top and the north pole on the bottom. And magnetic lines of force, as you know, this goes from north pole to south pole. These will be the magnetic lines of forces. However, if the electron is moving in the opposite direction, in this way, so situation will be exactly reverse. The north pole will be created at the top and the south pole at the bottom. So magnetic lines of force will be. So based upon the spin, you can see we are getting two different types of configurations. The first configuration is denoted by a magnetic quantum number ms is equal to 1 by 2, whereas the second one is denoted by minus 1 by 2. That means if we have a spin has also the spin quantum number has always value 1 by 2, and when we are applying a magnetic field, let's say in the z direction, so according to that it splits. So there are ms which can take values minus half or plus half depending upon the way the electron is revolving. Now electron is considered as a charged sphere spinning about its own axis. So due to that, it will possess some intrinsic angular momentum and it will also possess an interesting magnetic moment. We denote this one by S and this one by mu S. Now, the magnitude of this angular momentum in quantum mechanics is equal to where S is the spin quantum number, Ig is the Planck's constant, H by H cross means is H by 2 pi, and this value of S, as we have told, is always equal to 1 by 2. So the value of S comes out to be root 3 by 2 H cross. Now the component of Sz, as we have already told, is MSH cross. So as we have already told, MS is equal to either half or minus 1 by 2. Now, if we take a ratio between, okay, now what about the orbital angular momentum? So, as we have told that the electron is also revolving around the nucleus. So, in that case, we take the speed of the electron as v. This is the speed of the electron, and it is revolving around the nucleus. And this is a Bohr's orbit, so we take the radius as equal to a, and v is the speed of electron, and Bohr's orbit radius is a, and t is the time period of revolution, t. So t is equal to the circumference by the velocity. This is the time period. Now, as the electron is revolving around, so it constitutes a current. So that current I is equal to E by T. So if we put the values of T here, it will be E into V by 2 pi A, and the magnetic moment is equal to I into area. That means I into pi square mu. We call it mu L, the orbital angular momentum L, and it is equal to, the values, it will be EV by 2 pi A into pi A square. So it will be EV by 2 into A. So continuing, I is equal to EV by 2 into A, and if you multiply with the mass of electron on above and below, so we add here M by M, and we write it again as E by 2M into MVA. So this MVA is actually the orbital angular momentum L. So we can say that mu L is equal to E by 2m into L. We take the magnitude. Mu L is equal to E by 2m, and magnitude of L is capital L. So this is a relationship between the magnetic moment and the orbital angular momentum for the case of an orbital motion. For the case of a spin motion, that means if we take mu s by s, so it becomes actually twice of this value, mu L by L, because of the two different types of spins involved. And so we can, if we take the twice of it, it becomes mu s becomes equal to minus okay, right, 2 into E by 2m into s. So you can also write this one as equal. The negative sign indicates that mu s and mu are in the opposite direction. That means if this is your mu s, the s will be in the opposite direction. So that is indicated by this negative sign. And we can also write this one as equal to, if we take the magnitude, let's say, take the magnitude of mu s, I can write it as gs into E by 2m into s. So g is the spreading factor, the spin spreading factor, this gs. So then we write mu s to gs E by 2m into s. Now we know that s is equal to root 3 by 2 h cross. This we have already derived. So if we put the values here, it becomes 2 into E by 2m root 3 by 2 h cross square, h cross. So it ultimately turns out to be root 3 h cross by 2m, and we can write this one as root 3 into mu b, where mu b is equal to h cross by 2m, and there is a unit of angular momentum, and it is called Bohr magneton. So mu s has been found to be equal to root 3 mu b. So this was all about the spin-based electronics inside the atom. Now coming to a device, we will call that device is rather known as a spin valve transistor. Now, it looks like the following. With the silicon base, there are some metallic multilayers, and that again there is another silicon wafer. So this is a silicon. This is basically the collector. This silicon is the silicon emitter, and these metallic multilayers they form the base. So metallic multilayers mainly consists of there is a platinum, ohmic contact, metallic contact, followed by there is a copper and cobalt multilayers. So this is what the basis constitute is about. So the collector is actually forward bias and then emitter is reverse bias. This is the circuit. Now what happens is the electrons, they are injected into the metallic base. The metallic base, and they move across the Schottky barrier. That is, Schottky barrier means there is a semiconductor metal barrier. It is called a Schottky barrier. Metal semiconductor barrier. So there is a Schottky barrier here, and there is a Schottky barrier here. It crosses the Schottky barrier from emitter to base, and then it actually so from base to emitter, and then it passes through the spin valve. This is called the spin valve, and then it goes to the opposite side, which is the collector. This is how the model or the device works. Now, when the electrons are traversing the metallic base, these electrons are called hot electrons. The reason they're called hot because they have got they're above the Fermi level. Above the Fermi level, that is why they're called hot electrons. Now, the difference between a hot electron and a Fermi electron is the spin polarization of Fermi electrons depends on the density of states. Whereas this is not in the case of hot electrons. And whereas in the case of hot electron, it depends upon this is for Fermi electrons, I call it as Fe. For hot electrons, the spin polarization will depend upon the number of the density of the unoccupied state above Fermi level. Depend upon density of unoccupied states above the Fermi level. So if you look into the energy band diagram, so it is like this. This is the emitter side. This is the collector side, and this is the base. energy F. The barrier height of the collector side is 0.7 electron volt, and as for the emitter side and for the collector side is 0.6 electron volt. Now this emitter bias it actually accelerates electron towards the emitted barrier. They form what is called as hot ballistic electrons, and this is how they also need to cross this barrier. Now the probability of passing through the collector barrier. Now this probability depends upon collision of the electrons at the base, which affects the energy of the trajectory. Now for a base transistor with the ultimately what happens when after a certain time it passes through the base, whereas the energy is actually reduced due to the collision that is taking place at the base, which is made up of the multilayer cobalt and copper multilayers. Now, for a base transistor with a single metal base, this can be expressed by the following relation. For the single metal base, the transfer ratio of the current gain. Or you can also call it the transfer ratio alpha E, alpha O is equal to JC minus J leak by JC, and it is equal to alpha C for E alpha QM e to the power minus m by lambda, where alpha E is the emitter efficiency, alpha C is the collector efficiency, alpha QM is the quantum mechanical transmission factor, W is the base width, this is the base width, and this lambda, this is the mean free path of the hot electrons. Now the factor, this factor e to the power minus W by lambda, this factor represents the probability of transmission of the hot electrons through the base to the power minus W by lambda. It represents probability of transmission of the hot electrons to the base. And J in the previous, see just this J, this is the total collector current, and whereas, sorry, not this one. J is the total collector current, and JC is the total collector current, this one, and J leak is a collector leakage current, and JE is the injected emitter current, which JE, not JC. J is emitter current, and alpha E and alpha C will depend upon other types of and the quality of the semiconductor. These depends on the types and quality of the semiconductor. And in the spin wall transistor, under consideration of the thickness of the individual layers are much smaller than the spin slip diffusion length. So another point is that in SVT, the individual CU layers and their thickness is much smaller than spin slip diffusion length. Thickness smaller than spin flip diffusion length. So this means that this is the length traveled by the spins after flipping. That means if the spin is in this direction, ms 1 by 2, so it will traverse certain distance, to make ms is equal to minus 1 by 2. That means opposite distance. So however, the cobalt copper length or cobalt copper layer length is smaller than this distance. So this means that it avoids this spin flip scattering. So the current actually travels in, there are two current modes. So it implies there are two current modes corresponding to spin up and corresponding to spin down in an SVT.